Alright guys, time to do some more videos. This one is on the fundamental theorem of algebra. Sounds very, very important, doesn't it? Alright, let's do an example. Alright, we are going to graph and solve x cubed minus 5x squared minus 8x plus 48 equals 0. We're going to use our graphing calculator and put it in. It's going to look like this. So when we look at this graph, we see a 0 here, and we see a bounce here. So there are two distinct solutions at x equals -3 and at x equals 4. Alright, so now I'm going to factor this sucker. And the graphing calculator gives you a hint, and I'm going to let you use it on some of these problems like this. Instead of having to list all the possible rational zeros, you can use your calculator, narrow it down, and we're going to factor this down. So let's just go ahead and go with the -3, and we're going to divide this in to the polynomial. Like so. Remember, we can do the synthetic division. We're going to take the 0 right here, and then we're going to add 1 and nothing is 1, and multiply. -3 times 1 is -3, and add -5 and -3 gives me -8, and multiply. -3 times -8 is +24. -8 plus 24 is 16. -3 times 16 is -48. 48 minus 48 is 0. We know it's a 0. We can see it on the graph. We've just confirmed that it's a 0. But what we've also done is if -3 is a 0, then x plus 3 is a factor. And the other factor is this, 1x squared minus 8x plus 16. And now that we're down to a quadratic, we want to see if we can factor this sucker further. And if there's anything that multiplies to get 16 that also adds to get -8, we can factor it, which there is. So this is x plus 3. And then this over here is x minus 4 times x minus 4. So I'm going to put a little squared. And that little squared tells us that this has a multiplicity of 2. It has 2 solutions at 4. That's why there's a bounce here. So if we were to list all the solutions, we would say x equals -3, it equals 4, and then it equals 4 again. So it has 3 solutions, and that's because it is a third degree. So third degree, 3 solutions. One of those is repeated. The one that's repeated we say has a multiplicity of 2. Because it's in there twice. All right, let's do another one. Let's graph and solve x cubed minus x squared plus 16x minus 16 equals 0. This is a cubic function, so we know it's going to have at most 3 zeros. Let's look at the graph. So now we can see that it has one distinct 0 at x equals 1. And this means that there should be 3 total solutions, but we only have 1. What's going on with the other 2? Well, we're going to factor and solve now. We're going to use this 1 that we know, and we're going to divide it into the polynomial. All right, so we bring down the 1. 1 times 1 is 1, minus 1 is 0. 1 times 0 is 0. 16 and 0 is 16. 1 times 16 is 16, and then that makes 0. So what this tells me is that one of my factors is x minus 1. And then the other is x squared plus 0x plus 16. And x squared plus 16 does not factor further, so this is the polynomial fully factored. And when we say equals 0, if we set this one equal to 0, obviously we would get 1. We already know that. And if we set x squared plus 16 equal to 0, we could say x squared equals -16, x equals plus or minus the square root of -16. Therefore, x is positive and negative for I. That's 2 more answers. We needed 3 total. 2 of them are imaginary. So this is third degree. It has 3 total zeros. 1 is real, and 2 are imaginary. So that leads us to your fundamental theorem of algebra, which says counting repeated and complex solutions, an nth degree polynomial has exactly n solutions. Sorry, left out the word degree. Okay, write that down, and then let's do another example. All right, so how many solutions does 5x squared plus 3x to the fourth minus 6x to the fifth plus 7x to the third minus 1 have? I'm just asking how many does it have? You don't have to tell me what they are. You don't have to tell me what kind they are. All you have to do is know how many there are going to be. And we're just going to look at the degree. Don't be fooled. The 2 is first, but that doesn't make it the degree. The 5 is biggest, so the 5 is the degree. And if 5 is the degree, then there are 5 solutions. All right, now, this example says find all the zeros. That means all of them. When it says all, so the key word is going to be what they're talking about. And this one says all. That means all repeats, all imaginaries, all reals, all zeros of f of x equals x to the fifth minus 4x to the fourth plus 4x cubed plus 10x squared minus 13x minus 14. So it's already in standard form, and we can see that it's fifth degree. So that means we're looking for 5 total zeros. And the easiest way to figure out where to start is to use your graphing calculator. So graph it in the calculator and look at all the possibilities. Instead of listing your possible rational zeros, we're just going to cheat and use the graphing calculator. And here's what it looks like. I can see one bounce, which is probably going to count for 2, and then one cross through, which is going to count for 1. That's still only 3. But we know at least x equals -1 and +2. So we can use either one of these, and we're going to do some long division. I'm going to go with the 2 first since it's not repeated. And I'm going to do my synthetic division. We want to divide 2 into the polynomial, so we bring down the 1. Times 2 is 2, minus 4 is -2. Times 2 is -4, plus 4 is 0. Times 2 is 0, plus 10 is 10. Times 2 is 20, minus 13 is 7. Times 2 is 14. Minus 14 is 0. So that confirms that 2 is an actual 0. It also tells me that our polynomial factors to x minus 2. And then we always go down a power, so 1x to the fourth minus 2x to the third plus 0x squared, I'm going to go ahead and write it, plus 10x plus 7. But that's not fully factored, and that doesn't give us all the zeros. So that we really can't factor this any further by hand, so let's go ahead and use the next one that we know. Because we know another one, we know -1. I'm going to divide -1 into the remaining numbers, into the 1, -2, 0, 10, and 7. Don't go back to the original, because if you divide it into the original, yeah, it'll work, but we're trying to factor it down. We're trying to break it down as far as we can get it. So we need to use this. All right, so we're going to bring down the 1 times -1 is -1, minus 2 is -3, times -1 is 3, plus 0 is 3, -3, 7, -7, 0. That confirms it works. It tells us we have x minus 2 we had already. We have an x plus 1 for that. And then we have down another power would be 1x to the third minus 3x squared plus 3x plus 7. And this can't factor by grouping, so we still have to use some more division. Luckily, we understand that a bounce means a repeat. So I'm going to divide -1 again. This time I'm going to use these numbers, 1, -3, 3, and 7. Bring down the 1, -1, -4, 4, 7 minus 7, 0. Okay, I'm going to scroll all this up. Hold on a sec. All right, so we had x minus 2, and we had x plus 1 already. So these guys get to stay. This -1 tells me that we have another x plus 1. And then these numbers give me, down another power would be x to the second minus 4x plus 7. Okay, so we have this one and this one and this one are the real zeros that we can see. We have one real one and then one repeated real one. And then we need to know, there's 2 more, obviously. And if we can't see them, they're probably imaginary. So how would we solve for that? And you can use completing the square, or you can use quadratic formula. I'm going to go ahead and use quadratic formula. So this is a and b and c. X equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a is 4 plus or minus the square root of negative 12 all over 2. 4 over 2 is 2. Negative 12 is 2I root 3. And 2I root 3 divided by 2 would be I root 3. So 2 plus or minus I root 3. That's two different answers because that's two different complex numbers. So our total amount is 5, and they are, if we listed them all out, we would say negative 1, 2, 2 plus I root 3, and 2 minus I root 3. There's your 5 zeros. 2 of them are imaginary, and 2 of them, or one of them is repeated, and so that gives us a total of 5. Whew. All right, now, 1 plus the square root of 2 and 1 minus the square root of 2 are conjugates, and we talked about this before when we were rationalizing denominators. 1 plus 2i and 1 minus 2i are what we call complex conjugates. So, if you are given an a plus square root of b or an a plus bi as a 0, you automatically know that the minus of either of those will also be a 0. Because when you're doing the quadratic formula, or when you're completing the square and you're taking a square root, you always do a plus or minus for a square root. So, for example 5, it says write a polynomial of least degree with a leading coefficient of 1, so we don't have to have any crazy leading coefficients, and 2 plus the square root of 3 is zeros. So if I gave you a problem like that, and I gave you this as a 0, you would automatically know, okay, then our zeros are really 2 and 2 plus the square root of 3, and 2 minus the square root of 3. The conjugates are always, they always come in pairs, always. So we would write our factors. If 2 is a 0, the factor that goes with that is x minus 2. And if 2 plus the square root of 3 is a 0, then the factor that goes with that is x minus 2 plus the square root of 3. Note that I'm putting it in a parenthesis within there, in that factor. And then another factor is going to be x minus, because it's always x minus the 0. And then the other 0 is 2 minus the square root of 3. This confuses people a lot. The sign that we're switching out is this one and this one here. This is always minus. Your factor is always x minus the 0. Now it says write the polynomial, so we need to multiply all this fun stuff out. And I'm going to go ahead and take these two, and I'm going to distribute my negative, x minus 2 minus the square root of 3. X minus 2 minus minus makes plus square root of 3. And I'm going to FOIL these suckers out. So I end up getting x squared minus 4x plus 4 minus 3. You can do all that math yourself. You know how to FOIL. FOIL, FOIL, FOIL. It's a lot of fun. Then we get to multiply that by x minus 2. So when we multiply that by x minus 2, we end up getting x cubed minus 6x squared plus 9x minus 2. So that's really the easy part, the multiplying out. We already did that section, but what I'm trying to teach you now is if I gave you this as a 0, then you can write it x minus that 0 and x minus the conjugate, which will also be a 0. So here's another one. Write a polynomial of least degree. That means that that's the least amount of x's we're going to, just the lowest amount of x's you could possibly have, because you could have more, but we don't want more. With a leading coefficient of 1, and 5 and I are zeros. So if I is a 0, the conjugate of I has to be a 0, because our imaginaries always come in pairs. So it's going to be 5 and plus I and minus I. So our factors will be x minus 5, x minus I, and x plus I. And you should remember when you FOIL and you multiply your conjugates together, the i's cancel out. We get x squared plus 1, and we're multiplying that by x minus 5. And we end up with x cubed minus 5x squared plus x minus 5 as our polynomial. All right, now we're going to learn about Descartes' rule of signs. This is kind of tough, so I'm going to go slow. The number of positive real zeros, that means the amount of times that your graph crosses the positive x-axis, is the number of changes of sign for the polynomial, or less than that by an even number. The number of negative real zeros, that means how many times it crosses the negative x-axis, is the number of changes of sign for the function evaluated at negative x, or less, sorry, that should be less than that by an even number. So what I mean is here we've got x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x cubed minus 6x squared minus 8x minus 8. And I just want to know how many positive real zeros are there going to be? How many times is my graph going to cross on the right side without actually looking at it? So we count sign changes, and by sign changes I mean this is a positive x to the 6th, and then this is a negative, so that's one sign change. Then this is a negative going to a positive, that's another sign change. And that's a positive going to a negative, that's another sign change. And then we're going negative to negative, that's not a sign change. To negative again is not a sign change, to negative again is not a sign change. So we have 1, 2, 3 sign changes. So it says the number of positive real zeros is the number of changes of sign, so we got 3, or less than that by an even number. So we're going to subtract multiples of 2. So we say 3 or, and then if I took away 2, I'd get 1. And then if I took away 2, I'd be a negative. And we're counting things, so we're not going to be using negative numbers. So 3 or 1 positive real zeros. That means it crosses the x-axis on the positive side either 3 times or 1 time. For sure. Now we're going to figure out how many times it crosses on the negative side. And what we have to do is take the function and evaluate it at negative x. So, if I took negative x and raised it to the 6th power, it would still be x to the 6th. If I took, and then minus 2 times negative x to the 5th. If I take negative x to the 5th, I get negative x to the 5th. So the sign changes because negative times negative is plus 2x to the 5th. Then I'm going to use this one, 3 times negative x to the 4th. Negative x to the 4th is positive x to the 4th, so plus 3x to the 4th. So basically on all of your even powers, your sign stays the same as what it was no matter what. And on your odd powers, the sign switches. So when we have minus 10x cubed, and we have minus 10 times negative x cubed, then those negatives make plus 10x cubed. Minus 6 times negative x squared is the same thing as minus 6x squared. Minus, sorry, I'm running out of room, minus 8 times negative x gives us plus 8x. And then minus 8 stays minus 8. So now we count sign changes. And there's plus to plus, that's not a sign change. Plus to plus is not a sign change. Plus to plus is not a sign change. Here's one. Here's another. Here's another. So there's 3. It's not always going to be the same amount. It just happens to be that they were both 3 for this problem. Really, when you're doing this, this looks so complicated, but all you have to think about is keep the same signs on all of your even powers and switch them from what they were on all your odd powers, okay? So now we've got 3, and then less than that by multiples of 2 means 3 minus 2 is 1, 3 or 1, negative real zeros. All right, so now what does that do for us? Why do we even care? Well, let's look at the original polynomial. The degree was 6. Because of what we just learned, we know we're going to have 6 total zeros. All right, when I have a 0, that means that my graph could cross, here's your positives, your negatives, and then the only other option we have are imaginaries. So, if I have 6 total zeros, and 3 of them could have been positive, and 3 of them could have been negative, then there would be 0 imaginaries, right? We're looking at all of our combinations. If 3 of them were positive and 1 of them was negative, then we'd have 3 and 1 makes 4. That leaves 2 left to be imaginary because there's 6 total. If I had 1 positive and 3 negative, that would give me 4, so the remaining 2 would have to be imaginary. Or if I had 1 positive and 1 negative, because it's both of them are 3 or 1. 1 and 1 makes 2, and that leaves 4 to be imaginary. So our imaginary amounts will always be even numbers because they always come in pairs. So our possibilities that we could possibly have is crossing on the right side 3 times, the left side 3 times, and none of it being imaginary. Or 3 and 1 with 2 imaginary, 1 and 3 with 2 imaginary, or 1 and 1 with 4 imaginary. Okay, the very last thing I'm going to teach you today is finding zeros in the calculator. And this is easy. You're going to go to y equals, you're going to put the function in there, and then you're going to hit second calc 0 to find the actual values of the zeros. So as an example, let's do the one that we just did in example 7, and let's put that into our graphing calculator. It's going to look like this. So we had predicted that we could have 3 or 1 positive, and we have 1. We could have 3 or 1 negative, and we have 1. If we've got 1 positive and 1 negative, there's 4 left that have to be imaginary. But what I want to teach you right now to do is just to put this in y equals, graph it, and go second calc 0. It's going to ask you for left bound, so you'd put a left bound, right bound, and then guess. And this one is negative 0.732. And then you do it again, second calc 0, left bound, right bound, guess, and this one is going to be 2.732. And that's all. That's how you do it in the calculator. All right, I'm going to not give you a joke because I know you're probably tired of hearing me talk. Have a good day or night or whatever. Bye.